Welcome to the Calculusthenics number 3 help video. In this video, I'm going to work all the A problems, and hopefully that will give you some help with working the remainder of the problems on the assignment. So let's take a look at this first problem. The directions show us how to write a justification for the existence of a limit of f of x as x approaches c. So in this box, I've created kind of a little template for you to show you how to write that justification. And you'd write it something like this. You'd say the limit of f of x as x approaches c exists because the left-hand limit has a value, the right-hand limit has a value, they're equal to each other, and so therefore the limit exists. So let's take a look at number 1 and let's write this justification. It says, write a justification for the existence of f of x as x approaches 2 if f of x equals this piecewise function. So the function is defined as x minus 1 quantity squared when x is less than or equal to 2, and as 3 minus x for all x is greater than 2. All right, so to write that justification, let's just follow this template up here, and we'll start by saying that the limit of f of x as x approaches 2 exists because, okay, first let's show what that left-hand limit is. So we'll say the limit of f of x as x approaches 2 from the left, that would be the left-hand limit. So now if we're going to find that limit, if we're looking at approaching 2 from the left, we're going to use this part of the function because if we're approaching 2 from the left, we're talking about x values that are smaller than 2. So let's go ahead and just do the work right here. We're going to say that that limit is equal to 2 minus 1 quantity squared. 2 minus 1 is 1, and 1 squared is 1. So there's our left-hand limit. Now let's write the find the the right-hand limit and see if we get the same thing. So we'll take the limit of f of x as x approaches 2 from the right. Okay, now when x is approaching 2 from the right, those are the x values that are greater than 2, so we'll use this part of the function definition. So that would be, let's see, 3 minus 2, and 3 minus 2 is 1. So you can see that the left-hand limit and the right-hand limit agree. So we will conclude by saying, therefore, I hope you all know that the 3 dots means therefore the limit of f of x as x approaches 2 equals 1. So now let's take a look at number 2a, and in this problem, same kind of a problem, we're going to write a justification for the existence of a limit, the existence of f of x as x approaches 1. The only difference is this time, instead of being given an analytical definition, we're given the graph of f of x. So what we're going to do is start it the same way. We're going to say that the limit of f of x as x approaches 1 exists because, okay, as you look at the graph, we can see that as x approaches 1 from the left, this graph is approaching positive 4, and then same thing as we look at the graph as x approaches 1 from the right, f of x is also approaching 4. So we can see visually in this graph that the limit definitely exists. But let's go ahead and write our justification. So we'll say that the limit of f of x as x approaches 1 exists because, we'll say the left-hand limit, the limit of f of x as x approaches 1 from the left, we can see from the graph that that's equal to 4. And the right-hand limit, the limit of f of x as x approaches 1 from the right, is also equal to 4. So therefore, we can say that the limit of f of x as x approaches 1 is equal to 4, and therefore it exists. In problem 3a, we're being asked to write a justification for continuity. So let's look at how to write a justification for continuity of f of x at x equals c. So again, I'm going to recommend that you follow this template. It's going to look a little bit different than what we've done previously, but I think if we follow this template, we will be guaranteed to get all possible points if you were ever asked to write a justification like this on the AP exam. So let's just follow the template that says a function f of x is continuous at x equals c if the following conditions are met. Number one, f of c has to be defined. Number two, the left-hand limit and the right-hand limit as x approaches c from the left and the right have to agree. And then this is one step that I haven't required in the past, but I'm going to ask you to start writing from now on because I would hate for us to, for you to miss a point on the AP exam. Once you've established that the left-hand limit and the right-hand limit agree, I just want you to take one little extra step and say, therefore, the limit of f of x as x approaches c is equal to L. And then last, we've said that f of c is defined. We've said that the limit exists, and now we need to say that those two agree. So let's take a look at number 3a and give it a shot. It says determine if the graph of f of x is continuous at x equals 2 if f of x is defined by this piecewise function, f of x equals the square root of x minus 2 for all x's less than or equal to 2, and 1/2 x minus 1 for all x's greater than 1. So following our template, we're going to say that f is continuous at x equals, x equals 2 because, so we will say that f is continuous at x equals 2 because, and let's go ahead and just number our reasons. Number one, f of 2, well, let's figure out what f of 2 is. So we'll go to our function definition, and let's see, which part do we use? Well, here we use when x is less than or equal to 2, we should use this function definition, the square root of x minus 2. So that means that's equal to the square root of, I'm going to replace x with 2 and write square root of 2 minus 2, which is equal to 0. Okay, and then number 2, let's talk about the left hand and the right hand limit. So we're going to say that the limit of f of x as x approaches 2 from the left is equal to, well, when we're approaching 2 from the left, again, we're going to use this part of the function, okay, because as we're approaching 2 from the left, we're talking about x's that are less than 2. So we'll go ahead and evaluate that as a square root of 2 minus 2, which equals 0 again. And then the limit of f of x as x approaches 2 from the right is equal to, well, now that we're approaching 2 from the right, we're talking about x's that are greater than 2, so we'll use this part of the function definition. So we will take 1/2 times 2 minus 1. Well, 1/2 of 2 is 1, and 1 minus 1 is 0. So we can see that these left-hand and right-hand limits agree. So we need to add this extra step that I haven't required in the past, but I want you to include now. So we're going to say that, therefore, the limit as x approaches 2 of f of x is equal to 0. So now we can see that f of c is defined. It's equal to 0. The limit of f of x as x approaches 2 is also equal to 0. So we'll finish out with step 3, which says that f of 2 is equal to the limit of f of x as x, oh, I have to squeeze it in here, as x approaches 2. In problem 4a, we're going to practice writing justifications that involve the intermediate value theorem. So here's how you answer the question, does there exist a c on the closed interval from a to b such that f of c equals k? So to do that, the first thing you're going to do is evaluate f of a and then evaluate f of b. Then you'll check to see if your k falls between f of a and f of b, and if it does, then you'll write the following. You'll say yes, and I'm going to have you add this next little phrase that, again, I haven't required in the past, but the more I think about it and talk to people, I think we need to include this to make sure that a grader that's grading your work on the AP exam wouldn't take a point away from you. So we're going to say yes, by the IVT, which stands for, of course, Intermediate Value Theorem, and you can abbreviate it. Yes, by the IVT, there exists a c on the interval from a to b such that f of c equals k because, then you need to state these two reasons, because f is continuous on the interval from a to b, and f of a is less than k, which is less than f of b. So let's try that using this template on number 4 that says, given that f of x equals 2 times e to the x, Is there a c on the closed interval from -1 to 1 such that f of c equals 2? Okay, so the first thing we're going to do is we're going to evaluate f of a and f of b. So let's find out what f of -1 is, and then we'll evaluate f of 1, and then we'll see if 2 falls between those two function values. Okay, so let's first of all find f of 1, or excuse me, f of -1. That would be 2 times e to the -1 power, which is the same thing as 2 over e to the positive first power. And then e, by the way, e is approximately equal to 2.72. So if I were to, actually it's 2.7, hold on, I'm going to actually carry it out to a few more decimal places. 2.718, and I'm going to, it's called truncating. I'm just going to chop it off after 4 decimal places. And we'll talk more about that, about rounding and truncating later. But anyway, that's what I'm going to do for now. So now if I take 2 and divide it by 2.7182, we're going to get that our f of 1 is approximately equal to, let's see, 0.7357. All right. And then let's evaluate f of 1. So that would be 2 times e to the positive first power. So 2 times 2.7182 turns out to be approximately equal to 5.4365. All right, so since f of 1 is 0.7357, and excuse me, f of -1 is 0.7357, and f of 1 is 5.4365, we can see that f of that 2 definitely falls between those two numbers. So we can say, to answer the question, we can say yes. And don't forget to add this part. Yes, by the IVT, which stands for Intermediate Value Theorem, there exists a c on the closed interval from -1 to 1 such that f of c equals 2, because first we need to say that f is continuous. So f is continuous, and be sure to state where it is continuous. We can either, in this case, since e to the x is a exponential function which is continuous everywhere, we could say everywhere continuous, or we could be more specific to this problem and say f is continuous on the closed interval from -1 to 1. Okay, and because, now go over here to your function values and start with the smallest one. The smallest one is 0.7357, so I'm going to put f of -1 first, and I'm going to say f of -1 is less than 2, which at the same time is less than f of 1. In problem number 5, we're going to return to the idea of continuity and look at the other type of continuity question that you are likely to see on the AP exam. And this is the type of problem where you're asked to find either one or two values that would guarantee that a function is continuous, either at a particular point or everywhere continuous. So this problem is asking us to find a value of m that guarantees that f of x is continuous at x equals -3/2. So we have this piecewise function defined in terms of x, and we need to find the m that would make this function continuous at -3/2. So it's going to be continuous at -3/2 if the limit from the left of -3/2 agrees with the limit from the right of -3/2. So let's go ahead and find those two limits, or find expressions for those two limits. Okay, so let's start with the limit as x approaches -3/2 from the left of, I'm going to put parentheses around this, -mx minus 3. Now I chose that part of the function definition because as I'm approaching -3/2 from the left, I'm talking about x's that are less than -3/2. So I'd use this part of the function definition. Okay, and then let's do some direct substitution. I'm going to replace this x, I'm going to replace with -3/2. So -3/2 times -m would give us +3 3 halves, 3 halves m minus 3. All right, and so now let's find the limit of f of x as x approaches negative 3 halves from the right. So limit of, now, if I'm approaching, as x is approaching negative 3 halves from the right, now we're going to use this part of the function definition, because if I'm approaching approaching negative 3 halves from the right, I'm talking about x values that are bigger than negative 3 halves. So we'd use this part of the function definition. So that would be, I'm going to take x and replace it with negative 3 halves. So I'd have a, let's see, negative 3 halves squared times m, and then plus negative 3 halves. I guess I could have just written minus negative 3 halves minus 3. And then we're going to simplify that. So I'm obviously going to have to spill over into the next problem. So let's go ahead and do some arithmetic. When I take negative 3 halves and square that, that means negative 3 halves times itself. And negative 3 halves times negative 3 halves would give us positive 9/4 m. And then I'm going to go ahead and get rid of those parentheses, minus 3 halves minus 3. And then let's go ahead and simplify this negative 3 halves minus 3. Remember, 3 is the same as, I'm going to get a like denominator, so that'd be the same as 6 halves. So negative 3 halves minus 6 halves more would be negative 9 halves. Okay, and so now I have the limit as x approaches negative 3 halves from the left. Here's my limit in terms of m of f of x as x approaches negative 3 halves from the right. Now these two limits have to agree, so I'm going to set them equal to each other. So I'm going to take negative 3 halves m minus 3 and set it equal to 9/4 m minus 9 halves. I might recommend that you do these problems on a piece of notebook paper because they're taking up a lot of space. So to solve this equation for m, I don't know about you, but I don't like these fractions. So what I'm going to do is look at all my denominators and get a least common denominator and multiply through by that least common denominator. That'll eliminate the fractions. As I look at my denominators of 2 and 4 and 2, their least common multiple is 4, so I'm going to multiply both sides of this equation by 4, and that'll get rid of those fractions for us. So 4 times 3 halves m would give us 6m, minus 4 times 3 gives us 12, and that's equal to 9m minus, let's see, that'll be 18. And then solving this for m, I'm going to subtract a 6m from both sides and add 18 to both sides. So I would get 6 is equal to 3m, and then dividing both sides by 3, m is equal to 2. So we have found the value for m that will make this function continuous at x equals negative 3 halves. So finally, let's take a look at this is number 6a. And in this problem, we're being asked to find an a and a b that guarantee that f of x is continuous everywhere. So we have this piecewise function that's actually defined in 3 pieces, and there's 2 places, there's 2 x values where discontinuities could occur, and that's basically where the function changes from one definition to another. So we need to examine what's going on at -1 and at +1. So what we need to do is we need to take a look at the limit of f of x as x approaches -1 from the left. All right, and as x is approaching -1 from the left, that means we want x values smaller than 1, so we would use this function definition. So we need the limit as x approaches -1 from the left of negative ax minus 2b. We need that to be equal to the value of the function at -1. We need that to be equal to f of -1. And then the other place where a discontinuity could happen would be at +1. So let's take the limit of the function at x as x approaches 1 from the right, which means we look at this part of the function, and we need that limit as x approaches +1 from the right. We need it to be equal to the function value at -1. So let me write that out. we need the limit of, let's see, it would be ax plus b. As x approaches 1 from the right, we need that to be equal to the function value at positive 1. So let's go ahead and get an expression and function values for those. So the limit of negative ax minus 2b as x approaches negative 1 from the left. So where I see an x, I'm going to replace that with negative 1. Negative 1 times negative a would give us positive a minus 2b, and I need that equal to f of negative 1. So if I go to my function, and when x is equal to negative 1, I want to use this part of the function definition, and 3 times 1 cubed would be equal to 3. All right, and then let's take a look at the limit as x approaches 1, positive 1 from the right. So I'm going to replace this x with 1, and 1 times a is a. So I need a plus b to be equal to f of 1, and f of 1 would be 3 times 1 cubed, which is just equal to 3. Okay, so now I have my two equations, and I have two equations and two unknowns. I have a system of two linear equations, so I'm going to solve that system using elimination. And it looks like, oops, I have a mistake here, don't I? This f of negative 1, let me fix this. When I evaluated f of negative 1, 3 times negative 1 cubed should have given me a negative 3. You probably caught that. So let me fix that. So I need that a minus 2b to be equal to negative 3, and then a plus b to be equal to positive 3. Now I'm going to use elimination, and I'm going to subtract these two equations. When I do, a minus a cancels out, and then negative 2b minus another b would give me negative 3b, and then negative 3 minus 3 more would give me negative 6. Okay, and if I divide both sides by negative 3, I get that b is equal to positive 2. And now that I know what b is, it'll be simple to find a. I think I will use this equation, and I'm going to replace b with positive 2. And when I do that, a plus 2 equals 3. Well, a is going to have to be 1. Oops. A equals 1.